Hello, welcome to Fundamentals of Acoustics. This is the 6th week of this course, and in this week we will extend the discussion which we were having in the last week. So, last week we had concluded by introducing the concept of spherical waves related to monopoles, and in that context we had also developed an expression for the impedance of a wave which is travelling spherically in outward direction. So, we will continue this discussion on spherical waves, but before we continue that discussion, we will take a small detour because we had introduced this notion of impedance for spherical waves. So, we will have a little bit more discussion on impedance for spherical as well as for waves travelling in one direction Cartesian frame, that is for planar waves, and also how we can actually measure this impedance. So, that is how we are going to start, and then once this discussion is over, then we will go back to spherical propagation of one dimensional waves in spherical coordinate system. Our theme will be impedance. Okay. Now, for one dimensional spherical waves, we had defined or we had shown that the impedance of a wave which is travelling outwards is Z, and it depends on R and omega, and that can be written as 1 over j omega rho naught R plus 1 over rho naught C. Now, let us look at the impedance for one dimensional waves travelling in Cartesian frame, that is one dimensional planar waves. So, our aim is to find Z for 1D waves in Cartesian frame. Okay. So, specifically we will consider 4 scenarios. First is we will have a closed tube, okay. This is one scenario 1. Then we will also explore how Z behaves in an open tube. So, that is scenario 2. Then the third scenario will be what is the nature of Z in a tube which is infinitely long. So, infinite long tube. So, that is scenario 3, and the fourth scenario will be a tube, and here in scenario 1 the tube is closed with a rigid end. So, here the tube is closed, but it is not perfectly rigid. So, this is imperfect termination. So, this is 4. So, these are the 4 scenarios where we will see how Z behaves. So, then we will have an overall picture of how Z behaves in 1D Cartesian frame and also how it behaves for spherical waves which are in one dimensional spherical waves. So, that is there. Okay. Okay. Now, so closed tube looks something like this. At x is equal to 0, this is a rigid termination. This is x is equal to minus L, okay, and our positive x direction is going towards the right, starting from rigid termination end. We should know what is it that we are trying to achieve. So, our aim is to calculate z, which is a function of x and w, and earlier we had defined z as, so z is a function of complex pressure amplitude and complex velocity amplitude. Okay. So, it is a function of p x omega u x omega. It is not a ratio of the, because these p and u are functions. So, they change with frequency and they change with x. So, it is not a number, but rather z is a function and it depends on p and x. So, our aim is to figure out p x of omega, p of which depends on x and omega, and u which depends on x and omega, and then we can calculate z. So, now we go to transmission line equations. So, p, so if I am being strict mathematically, then p essentially depends on x, time and omega, x, time and omega. Okay. So, in earlier lectures I had not written like this x, time and omega, I had just written x and t, but if you are mathematically more precise, then this is the way it should be written. So, this equals, so these are transmission line equations, p plus, p minus, p plus, p minus. So, p plus and negative of p minus divided by z naught e minus j omega x over c e j omega x over c. So, here what I am doing is I am right away assuming that s is equal to j omega, okay, and then e to the power of j omega t. So, we are assuming that s is equal to j omega. Okay. Now, at x is equal to 0, velocity, so velocity is 0. This is from the boundary condition. From boundary condition for closed end. So, if velocity is 0, then u, which is the complex velocity 0 t omega, is also 0, which means, so p plus by z naught e minus j omega x over c minus p minus over z naught e j omega x over c e j omega t, and this thing in the brackets, if it is evaluated x is equal to 0, it is 0. Okay. So, this is 0. So, one thing is that e j omega t cancels out, and when x is equal to 0, these term become 1. Okay. So, what I get is p plus minus p minus divided by z naught is equal to 0. Therefore, p plus equals p minus. So, let us call this equation A and this is equation B. So, now what we do is we put B in A. So, our modified transmission line equation. So, equation A is the general transmission line equation and it is valid for all sorts of boundary conditions. But now, the moment we put B into A, the modified form of transmission line equation will be specific to the closed tube. So, TL equations for closed tube so this is complex pressure x t omega, complex velocity x t omega equals p plus p minus. So, p plus equals p minus. So, I am just p minus. So, I am putting that equality and this is negative p plus over z naught. This is also divided by z naught e minus j omega x over c e to the power of j omega x over c e j omega t. So, what I can rewrite this as p x t omega equals p plus e minus j omega x over c plus e j omega x over c e j omega t. Okay. And complex velocity is p plus divided by z naught e minus j omega x over c minus e j omega x over c exponent j omega t. Okay. So, the relation for pressure I can further. So, this term in parenthesis is exponent minus j omega x over c and exponent j omega x over c. So, when I resolve them into their real and imaginary parts, the imaginary parts cancel out. So, I am left with is 2p plus cosine omega x over c e j omega t. Okay. And likewise for velocity I get 2 j and there is a negative here p plus sine omega x over c exponent j omega t. Now, this part is the complex pressure amplitude P of x and omega, and this part is complex pressure amplitude, complex velocity amplitude of which depends on x and omega only. Okay. Why do I say it is the complex pressure amplitude? So, the amplitude of this pressure is amplitude of this term in the circle times amplitude of exponent j omega t, right. And what is amplitude of e to the power of j omega t? It is 1. because what is e j omega t? Sin omega t plus j cosine omega t is cosine omega t plus j times sine of omega t, and its amplitude is 1. So, whatever is the amplitude of this p x t omega will be actually same as the amplitude of p of x omega, because the amplitude of this component is unity. Likewise, the amplitude, complex amplitude of velocity is this term in the circle. It is this term in the circle. So, with that understanding, we say, and then we have defined Z, which is the impedance, specific acoustic impedance, and that is defined as complex amplitude of pressure divided by complex amplitude of velocity. So, this equals 2 p plus cosine omega x over c divided by 2 j p plus sine omega x over c, and there is a negative here. So, this becomes, so p plus cancels out, 2 cancels out, and if I take j in the numerator, if I multiply and divide this numerator and denominator by j, I am left, this negative sign also goes away, and I am left with j. Oh, there should be a z naught here. So, there is a z naught in the numerator. So, z naught cotangent of omega x over c times z naught. So, z of x and omega equals j z naught cotangent omega x over c. So, this is the relation for specific acoustic impedance for closed tube. So, what does this mean? So, some observations. So, first what we will do is we will plot the magnitude of Z for using this relation. Okay. We will plot the magnitude of Z using this relation. So, what is the value of, so the magnitude will be z naught. Actually, I am not going to plot the magnitude of Z, but I will rather plot z over j, so that I just worry about the real component. Okay. So, at x is equal, and I can normalize it by z naught. So, at x is equal to 0, the value of this thing is going to be infinite, right. At x is equal to 0, the value of this is going to be infinite, and so let us calculate it. When omega x over c equals pi over 2, then x is equal to c pi over 2 omega is equal to f lambda pi over 4 pi f. So, this is equal to pi cancels out, such lambda over 4. Okay. So, when x is equal to lambda over 4, omega x over c is going to be pi over 2, and cotangent of pi over 2 is going to be 0. So, x omega x over c and cotangent of omega x over c. When x is 0, omega x over c is 0, cotangent omega x over c is positive infinity. Lambda over 4, omega x over c is pi over 2, this is 0. When x is lambda divided by 2, half of the wavelength, then this is pi, and cotangent of omega x over c is minus infinity. Then we have 3 lambda over 4, this is 3 pi over 2, it is 0, and then lambda, this is 2 pi, and this is positive infinity. So, the figure is going to repeat itself after lambda, right, and how is it going to look like? So, at 0 it is going to be very large, and then at pi over 2 it becomes 0, and then at, so let us draw some So, here I am going to, on the x axis I am going to plot omega x over c. So, let us say this is 0, pi over 2, pi, 2 pi, 4 pi, and so on and so forth. Excuse me, I will not call this. So, this is 3 pi, and the next one is 4 pi. So, my curve is going to look like so it starts from positive infinity, at pi over 2 it becomes 0, at pi it becomes negative infinity, okay, and then it comes back and this is the asymptote, it comes back like this, right. Then from 2 pi so it goes like this, right. So, this is how the impedance looks like, this is how the impedance. So, it repeats after every wavelength impedance. So, as so this is the closed end, as I am travelling in this direction in the closed end tube, at this point the impedance is positive infinity, then it goes down to 0, then it becomes negative infinity, and so on and so forth, and then again. So, that is how it behaves. So, this is how impedance behaves for a closed tube, and what we will do in our next class is we will develop a similar expression for an open tube. So, with that we close the discussion for today, and we will meet tomorrow again. Thank you.